What we're going to do in this video is we're going to solve rational equations very similarly to the way we would solve linear equations. So what I have is a couple of examples here. And what we're going to do is we're going to solve these as we would. So of course we're going to distribute the negative. So I've got 11x minus 6x plus 5 is equal to 40. Then we would combine my like terms. We would subtract the 5. And then we would divide by 5. So that's pretty easy. When we have no fractions as our coefficients or in any of our terms, we can simply get to that number pretty quickly. Same thing here. So go ahead and distribute. Just as a quick review, go ahead and distribute. I'm going to let you pause the video and then I'll put up the answers. And again, distributing the negative through the parentheses and combining like terms on both sides, we get an x is equal to 7. So what we're going to look at now is what happens when we have rational expressions or fractions in each of our terms. We can use the old rules of fractions to solve this and to combine like terms and move to the other side of the equation. But one of the methods that we can use is using the LCD to solve. So the first thing we have to evaluate is what is the LCD for each one of these. Now I've started with these two problems where we look for the lowest common, don't forget that's denominator. So when I'm trying to figure out the lowest common denominator, it only refers to the numbers in the bottom. So here I'm looking at the 3, I'm looking at the 2, so the lowest common denominator is 6. Now if you'll notice I have blanks here for variables and blanks here for polynomials, and we'll get to that in a little bit. But looking also at this one, between 6, between 8, and 4, we got to think what number. Remember, we're looking for lowest common denominator, which is another word for lowest common multiple. So we're trying to figure out what numbers do 6, 8, and 4 divide into, or if I carried those things out, and hopefully you land at 24. Regardless of what the LCD is, again, we can have variables and polynomials, but we'll get there in a minute. What we're going to do is our objective is to get every single polynomial, or excuse me, every single term in our polynomial to be over the same denominator. Now, if you'll notice, that is also including my whole number answer. A lot of people forget to take care of that, or whole number term. A lot of people forget to take care of that. So I have to make sure that I use it on every single term here. So going back to the old fraction rules, between here and here, between the 3 and the 6, this needs to be multiplied by 2. Between here and here, the 2 needs to be multiplied by 3, and as always, we're multiplying the top by whatever it's missing. So remember, this is 2 over 1. Well, 1 to go to 6, it needs to be multiplied by 6, so I also need to multiply this by 6. This is going to back to old fraction rules. I do have a video on my YouTube site if you happen to need some refreshers on finding lowest common denominator and getting them all to be the common denominator. So what I have now is now instead of x over 3, I've got 2x over 6. This is going to be 3x over 6, and this is going to be 12 over 6. Which is really cool. Now they're over the same lowest common denominator. So on this problem, what I'm going to do is explain where and why what we're doing. What I'm doing is basically now I'm getting rid of all the denominators. I'm going to show you why that's possible. So in essence, what we're doing is I'm multiplying both sides by that lowest common denominator. So when I distribute, this comes over here and this becomes 2x. And multiplying this, distribute here, so this becomes 6 over 6, so that cancels out and becomes 3x. I distribute it here, this becomes 6 over 6, so these cancel out, and it becomes 12. And now look, this is a nice, pretty, lovely integer problem like what I just did at the top of the page. And I can solve it like I did before. So I've got this is equal to negative 12. And then I'm going to divide both sides by negative 1. So this is why we multiply both sides by the LCD. It works, but I'm going to show you an even nicer shortcut. So let's do this again. Let's do the same idea with the fact that this is now 24 is the LCD. So we're going to do this whole thing again. I want this to be over 24, I want this new one to be over 24, and I want this to be over 24. So this first one going from 6 to 24, I need to multiply by 4. So I'm going to multiply this by 4. Now remember, we're multiplying by the whole thing, so there's some distribution that's going to have to happen here. So 8 to 24, I've got to multiply by 3. 4 to 24, I've got to multiply by 6. And again, we're multiplying the entire thing by 6, not just the x or the 5. So doing the distribution, this is 4x, and 4 times 3 is 12. 3 times 3 is 9. There's no x's in this one. And then don't forget, I've got a negative 6 multiplied by x. And I've got a negative 6 multiplied by negative 5. So we don't have to do this. This first problem is to explain why or how. But what we're doing is basically once they're all over the same denominator, we can simply cancel them out. You don't have to do this distribution. This was explaining why. But once we have them all over the same denominator, then the denominators are gone. So I have 4x plus 12 equals 9 minus 6x plus 30. And then we go back to our linear equations. I'm going to combine like terms. Oops, this is going to be 39 once I combine it. And then I'm going to pull this over here, so this becomes 10x. And over here becomes, subtracting 12, this becomes 27. So I have x is equal to 27 over 10, or x, get that out of there, x is equal to 2.7. So let's go down to the next one. Now I'm looking at denominators that have variables in them. So let's find the LCD. So again, we're going to use these in different pieces. So when I'm looking at the numbers, again, we only care about the denominators. So the only number I see in all the denominators, or this whole number means it's over 1, is 2. So 2 is going to be part of my LCD. And then I see another piece. I see that x is in my LCD. I have an x here and an x here. Now we don't have to account for both of them. We just have to pick what is the largest between them. And so there's 1 here and 1 here. So the most is just the 1. So when we create our new LCD, we know that the 2 is part of it, the x is part of it. Now, what is in the numerator? I don't care. I never care about what's in the numerator at all. So we're simply going to make this over 2x. We're going to make this one over 2x, with the plus in between, and then we're going to make this one over 2x. So this one, 2x, it didn't need to change, or I could multiply by 1, but either way, it's going to stay 5 over 2x. Now this one needed 2x. So this became 6x. This one, go from x to 2x, it needed a 2, so I got to multiply this by 2. And we're back to the same position where they're all over the same denominator. So I can cancel them all out. So I have 5 plus 6x is equal to 8. And then again solving. So 6x is equal to 3, subtracting 5 from both sides, and x is not equal to 2. Remember, we divide by the coefficient of x. So x is equal to 3/6, or 1/2. Okay, so now we're going to look at the next one. Again, the LCD is composed of different numbers, different letters, and different polynomials. So looking at the numbers, I only care about what's in the bottom. So I'm looking for the LCD between 6, 3, and 4. Pause the video, and hopefully you know it's 12. When it comes to the variables, I have 1x here, I have 1x here, and again, it's the most. So there's only 1 of each, so I only need 1 to account for everything. If I said x squared, it would just make my variables a little bit more complicated. So everything has to go to 12x, that new LCD. And if I've chosen the right LCD, there should be an easy multiplier on every denominator. So this one, from going from 3x to 12x, this one needs to be multiplied by 4. And whatever we do to the bottom, have to do the top. That's old school fractions. Okay. Pause the video and find the other fractions. Hopefully this is what you ended up with. So again, pause the video, see if you can't get the final answer. Cross out all the common denominators and get the answer. Hopefully you got x equals 2. So now we have a new situation. Now I have polynomials on the bottom. And this is a unique situation because we can't count the individual numbers and individual letters that are in polynomials. Once we look at the denominators. I don't have any variables that are by themselves, meaning that are just factors. We're looking for variable factors, polynomial factors, number of factors. And this x is part of a polynomial, so it's not part of that. This 1 is part of a polynomial, so it's not something that I account for here. So the only polynomial I have is x plus 1. And again, there's 1 here, and there's 1 there. So that's all I need, is to have the 1 and the 1. So I only need one of them. So just like with always, they all have to have x plus 1 on the bottom. The first one already had it, so it doesn't need to change. The last one already had it. It doesn't need to change. But the middle one does need it. So I need to multiply this by x plus 1, and this needs to be multiplied by x plus 1. So when we put this one here, we have to remember to distribute. So it's 4x plus 4. Now they're all over the same denominator, and finish the problem. Hopefully you got x is equal to -1. Looking at the next one, we still need to look for individual numbers, individual variables, and individual polynomial factors. So when I'm looking at the numbers, the only number that I have to account for is this one because it's multiplied. This one is in a polynomial. This one is in a polynomial. Remember, polynomials are terms that are added or subtracted, and this one's part of a polynomial. So the only the only number that's by itself as a factor is 2. There are no variables that aren't added. So there's nothing here. And the polynomials, well, I have x minus 2. I also have x plus 3. They're different, unique polynomials. If they're not exactly the same, then I have to account. And always, when I have one here and one here, we always are looking for the most. So if this, for example, I'm going to do an example. If this one had 1 here and this was squared, meaning there's 2 of them here, then I would do 2, not a total of 3 for 1, 2, 3. I would simply say I have 1 here, 2 here, so the most would be 2. But that is not our situation, so let's go back to our actual problem where we had 1, 1, and now I have 1 in my polynomial, or excuse me, in my LCD. So that means my polynomials, all of these terms have to have an LCD of x minus 2, x plus 3. And it gets a little long, x minus 2, x plus 3. And 2x minus 1, excuse me, x minus 1, silly, x minus 2, x plus 3. And then we evaluate. Well, this has got the x plus 3, this first term, but the 3 was already there. And what I need is to multiply it by 2, and I need to multiply it by x minus 2. So 2 times x minus 2. This needs 2 times x minus 2. And now this looks exactly the way it's supposed to look, like my LCD. This one has the 2. This one has the x plus 3, but it needs an x minus 2 on top and bottom. This one has the x minus 2, but it's missing a 2 and an x plus 3. This is missing a 2 and an x plus 3. So all of these into account. So I have 5 times x minus 2 plus, and then I have 1 times 2, so 2 times x plus 3. And once again, they are all over the same denominator, so I can cross them all out. So I now have, this is 6 distributed, so I have 6x minus 12, because I'm taking 3 times 2 and multiplying by x and by negative 2, equals 5x minus 10, if I distribute that through, plus, 2x plus 6. So what we're going to do is combine like terms on the right side, making that 7x minus 4, and then continuing just to solve our regular algebraic equation. That brings us now to changing the color. I don't know why the color changed, but that changes now to x minus 8. This next problem, I have x minus 4 and x plus 2. There are no individual numbers or variables that are factors. These are all only x minus 4 and x plus 2. There's 1 here, there's 1 here, there's 1 here, and there's 1 here. There's no clusters. The only way, again, I would include more than 1 in my polynomial LCD is if I had, for example, another x plus 2 down here. then I would have to include the other x plus 2 here. But we don't have that situation, so let's get that out of there. Okay, so pause the video. I want every LCD, every denominator, excuse me, to be the LCD. So we've got the common denominator, so multiply top and bottom to make these equivalent. Pause the video. Hopefully you got to that point. Don't forget to distribute the -5 throughout both parts of the polynomial. You don't want to have -20, and finish solving it. So hopefully you got this down to x is equal to a -4. Excuse me, x is equal to a +4. So what I'm going to do is pause for a second and talk about what we haven't yet, which is what problems or what values of the domain would actually work. We've just kind of done the number crunching and found the correct answer, but we have to see if this answer will work. And I haven't really addressed that, but I want to show that if I happen to put this value, this x equals 4, into my denominator, that actually makes a problem. So if I put it in here, if I have 4 plus 2, again we said x was 4, then this is, excuse me, this is 6 and that's fine. But if I put 4 minus 4, that becomes 0. And what happens is I multiply, my denominator will now be 0, which hopefully we know that any denominator of 0 means it's going to be undefined. So if x was, for example, in this one, if x was 4, then 4 minus 4 makes that 0, and 0 times anything would still be 0. The other one that's problematic, think what value would make this binomial 0, this one right here. Well, hopefully you know it's -2 would make that 0. So if I ended up with a answer of -2, this would also be problematic. So what I have to remember to do is not only do I have to look at the answer, but I also have to look at the domain. The domain, and a lot of times we see this, is usually all real numbers. But in this case, it's all real numbers except, well, again, 4 in this situation would be problematic. Anything that makes a binomial or the denominator 0. So 4 won't work. And we just talked about how in this binomial that -2 wouldn't work. So because the number I got is something that's a problem, it's one of my problem children, there is actually no solution. So that's one thing to keep aware of, and we will talk more about domain and range, domain restrictions, excuse me, in class. But just always check, especially when you're solving for variables in the denominator, that you check against the domain or any restrictions on that. Now we're going to do this next one here. And it looks like I have 3 polynomials in my LCD. Boom, boom, and boom. But I want you to factor this one. When I factored it, it actually becomes one of these 2 binomials. So now my polynomials are x plus 4 and x plus 3. We don't have any standalone numbers. We don't have any standalone variables. So all I have is I want every single denominator to have both of these polynomials. Okay. So figure out what is needed between both. Pause the video and we'll check ourselves. Hopefully you got these values. And then putting these into polynomials, we have 5x plus 15, distributing that one, 3x plus 12, distributing that one, and this other rational expression on the other side didn't need anything to be multiplied by. So I'm simply finishing it out, subtracting 19 from both sides. I get 8 over here, subtracting 8x from both sides, I get 4x. So x is equal to 2. Now this is the solution I got. So what I have to look in each binomial and see, does 2 make a problem? If I did 2 plus 4, that doesn't equal 0, so that's okay. 2 plus 3, that doesn't equal 0, so that's okay. So we're always going to check and make sure that the answer you got doesn't conflict with the domain restriction.